All right, this is going to be the video for Calc 3, section 16.4 on Green's theorem and the concept of circulation. So let's go ahead and get started. So first we're going to talk about, this is all applies for vector fields. If you have a vector field, sometimes that vector field will cause things inside of it to rotate. If you think about it as a vector field with some sort of physical force, like say a water flow field or something like that, something that's importing a force on something. Right, so consider these three 2D, two-dimensional vector fields. Here we have vectors that they're getting larger. The force, if you think of this as a force field, the force is getting larger as we go away from the origin, and everything is rotating kind of in a clockwise direction. Reverse over here on this one, everything's kind of rotating counterclockwise, but getting larger as we go away from the origin, and then everything is just steadily moving in a upward right direction here. Right, given by these particular definitions of fields. Okay, so those particular fields, if we were to compute a line integral around a closed circular path, then over here you would have that we're always going against the field as we go this direction, right? We're always going against the arrows, so we would have some sort of negative contribution for all the places along the path, and we would have a net negative integral around a closed path like that. Okay, this one over here, everything is always moving in the direction of the force field, so everything would be positive, adding up, and we'd have a net positive. But in this case, what would happen is for half the circle, we would be moving generally against the flow, and then for the other half, we'd be moving an equal amount with the flow, and so the sum would sum to zero. Right, so we're going to define something about these three things called circulation. So the concept of circulation is, imagine if you were to put like a beach ball in the center of this. Let's start with this one over here, the positive circulation, and you put it here at the origin. Then because all of the vector's forces are circulating in a counterclockwise direction, in other words, in the direction of positive angle increase for trig angles defined from the positive x-axis toward the y, then we're going to define this sort of behavior as positive circulation. So something which causes, if it was a force, to rotate in the counterclockwise direction in the same direction as angles increase in trig, that's defined as positive circulation. And if you were to put a beach ball in the middle of this over here, then it would rotate in the clockwise direction. So we define that as negative circulation. Right? And if you put a beach ball in the middle here, it wouldn't rotate at all. It may translate, but it's not going to rotate. So this is called zero circulation. So conceptually, that idea that the vector field could cause something to rotate if it was a force field is called circulation. It applies whether we're talking about force fields or not. The concept is general. All right, so if you were to take something that has positive circulation, so the beach ball at the center would definitely rotate in a counterclockwise way. It turns out that other beach balls around here for this type of a field where the magnitude of the force vector is increasing as we go away from the origin in every direction, even if I pick a beach ball out here, like say this beach ball out here, and look at that, so we're blowing that up, that beach ball will also rotate counterclockwise. And the reason for that is due to an imbalance in the forces, right? Below that particular beach ball, right, the forces are smaller, and then they're larger on this side. And because of that imbalance, although there's a push to the left, there's more of a push on the top and less of a push on the bottom, which causes a net rotation that's counterclockwise. And the same thing for the vertical fields. If there's more on the right compared to the left, then there'll be an imbalance that causes a net positive circulation. So a field such as this would still produce a counterclockwise circulation, not just at the origin, but at any point in the field. Okay. All right. So really, circulation has to do with imbalances in the forces as you are at a particular point. And maybe we could refer to that as microscopic circulation. In other words, there's an infinite number of points here, and at every point there's a little circulation. In this case, all of those circulations would be positive. All right. So if you consider that you had every point in a region within a vector field that has positive circulation, then there would be little positive circulation, microscopic circulations all throughout that field. And then if you're taking a vector line integral or path integral here that goes along a curved path through that, place, right, around in a counterclockwise way in the direction of positive circulation, then you can think of the vector line integral as the sum of all of the little microscopic circulations that are enclosed. In other words, this has a circulation, and it's really the sum of all the little circulations inside. That turns out to be provably true. And we're going to express that as an idea called Green's theorem, who discovered this. There's a website here, mathinsight.org, that has a lot of interesting visualizations and things. When I went to it recently, it seemed like it was down, but if it functions for you, you can check that out to get a little bit more insight into this. But we're going to think of this as the total circulation around a closed path is the sum of all the little microscopic circulations inside, okay? And that idea is expressed in a double integral called Green's theorem. But let's further, in order to be able to use an integral to sum those microscopic circulations, we have to have some sort of mathematical expression for this concept of circulation. So let's take this imbalance idea a little bit further. Okay, if we have a point, right, and there's more force on top of the point than on the bottom, I'm just going to consider the horizontal field right now, then the arrows that are pointing in this direction are pointing in the negative x direction. So there is a, so if I have a force vector, or force field, which is a vector field, which is defined with the letters p and q for its x and y components here, then this horizontal force would be what's happening with this component, because that's horizontal. And a force to the left would be in the negative x direction. So if this is changing, then that means that the amount of force in the negative p direction, the change in the amount of force in the negative p direction, may be changing as I move in the y direction. In other words, maybe it's small here, and then it gets larger and larger and larger, which means that p in the negative direction is changing as I change in the y direction. So I can represent that as a slope or as a derivative, right? It would be the negative partial derivative of p with respect to the y direction. That basically means, is there an imbalance? This is caused by an imbalance. So this would be positive if there's an imbalance which causes rotation this way. That term, negative partial derivative of p with respect to y. And the vertical components would work similarly. If you look at this vector, this is in the y direction is q, then if q is changing and getting larger as I change in the x direction, the partial derivative of q with respect to x would, if that was positive, it would be an imbalance, which is causing a counterclockwise positive circulation. Okay, so if I just sum those two things up, that's going to give me some measure of the total amount of positive circulation. So if I take this term, so it's negative partial p with respect to y plus this term, and then we're just going to change the order and call that partial q with respect to x minus partial p with respect to y. That term gives me the amount of positive circulation in a field at a particular point. Okay, does it seem a little bit familiar? Because it's really close to our conservative field test, right? We said that if partial qx equaled partial py, that meant that we had a conservative field, and we know conservative fields, actually, that means, therefore, that they have a circulation of 0, because these two things would be equal. There's no overall circulation in a conservative vector field. Okay, so now we can say, well, a vector field is conservative if its circulation is 0, because that's the same as saying our test that a partial derivative of q with respect to x is equal to partial derivative of p with respect to y. But more importantly, this gives us an expression for summing up a microscopic circulation. All right, so now what we're going to say is, if I sum all the microscopic circulations, and those circulations are represented by my new expression for circulation, if I sum that over a two-dimensional area that's enclosed by a curve, then that will equal the value of the line integral along that curved path. So there's some intuitive things here, maybe not intuitive, but can be provably true, that the line integral around a counterclockwise closed path in a vector field represents the total circulation around that path. And that is equal to the sum of the microscopic circulations over the area. This result is known as Green's theorem, named after the mathematician who discovered it, Green. Okay, what that means is we can take a one-dimensional line integral around a curve and instead do it with a two-dimensional area integral. Okay, and many times it's easier to do this 2D integral than the 1D integral. So this is going to turn out to give us yet another way to evaluate path integrals in a more easy fashion. But this is only applicable if we have a curved path. In other words, it has to start and end on the same path. And we're only going to use this when we don't have a conservative vector field, because if I have a conservative vector field, then I know that the sum of the closed path, the integral along a closed path for a conservative vector field always sums to 0. Okay, so because this only applies to a curved path, a lot of times we modify the integral symbol over here. We put a little circle here indicating this is over a closed path, or some books, they put a circle with an arrow to indicate a direction, because technically this is for positive counterclockwise. If in fact you want to integrate a line integral around the clockwise path in the xy plane, then you have to multiply the result by -1 to account for that change in direction of circulation. All right. So that's Green's theorem, and we're going to add it to our tree. If we're trying to figure out how to evaluate a line integral, first we ask it, is it scalar or vector? If it's scalar, we use our scalar function. If it's vector, the next question we ask is the field conservative, by checking partial py, partial qx. If it's equal, that means that it's conservative, which means we can find the potential function and evaluate with the fundamental theorem of line integrals. If it's conservative and we're going around a closed path, then it would be 0, right? If the field is not conservative, then the next thing we ask is the path closed? And if it is closed, now we can employ Green's theorem. And then only if it's a vector field that's not conservative and not along a closed path do we have to resort to the more general case here, where we have to parameterize the curve and all of that, okay? All right, and do the full vector dot product of the parameterized curve method. All right, so we're going to look at some examples here. This first one's already worked out for us. It says evaluate the line integral A directly and then B using the Green's theorem. So this is a vector field expressed with a P and a Q here. And this is along a closed path, circle with center at 0, radius 2. So here's the path. We can choose to make that positive. So we'll go in this direction, okay? And first, let's just do it directly. So that means we're going to ignore Green's theorem, okay? So the P is x minus y, the Q is x plus y. First thing we would check is whether or not it's conservative, because if it's conservative and we go along a path, we know that it sums to 0. Okay, so dp dy, well, that turns out to be -1. dq dx turns out to be +1. Since those don't match, this is not conservative. So we're not going to be able to do this with a, well, we know that this is not going to sum to 0. And we also know that we can't find a potential function for this to use the fundamental theorem. So I'm going to have to go all the way down here to this method here and parameterize the curve and do the dot product. All right, so we would parameterize the curve. Our standard parameterization for a circle is that x is the radius times cosine t, where t is the angle. So 2 cosine t, y is 2 sine t, where we have t go from 0 to 2 pi counterclockwise around this path. Okay, and that means our position vector here is 2 cosine t, 2 sine t. So the tangent vector is the derivative of that. Cosine is negative sine, the derivative of sine is cosine. And that means that we can plug in the position vector x and y to the field, right? F is given by x minus y for the x component and x plus y. So we have to replace these x's and y's with the values here from the position vector, parameterize it. And we get this, and when you carefully boil it all down, right, we end up getting this. Right, but you end up with sine squared plus cosine squared here, which is 1, and you have a -4 sine t, cosine t, and a +4, so these cancel, and this ends up just being the value 4. So when you take the dot product, this part here, this dot product, then you end up getting 4. So we're integrating 4 around the parameter, and the parameter goes from 0 to 2 pi. So there should have been a dt here and a dt here, and then that becomes 8 pi. So this wasn't too terrible to do kind of the long way, but the value here is 8 pi. All right, so what we're saying is that really represents the sum of all of the microscopic circulations inside that path. And we found it by actually parameterizing the path and evaluating this integral directly. Okay, so now let's do the same thing, but this time we will use Green's theorem. Okay, so we have our P and our Q, right? We're going to find the expression for circulation, which is dq dx dp dy. So dq dx was 1, and dp dy is -1. And so the expression for circulation turns out to be 2. And so that means we can take this integral and instead represent it as a 2-dimensional integral over the region enclosed of the circulation. So now I just have to enclose this with a 2D. So the integral setup's a little tougher. I would use polar in this case. And we'll go from r equals 0 to r equals 2. And the dA element would become r dr d theta. And then we would go 0 to 2 pi to cover the region. So we're just integrating 2r from 0 to 2 and 0 to 2 pi. This one is, you can separate and factor the two ones separately. Do the integration and plug in, and you get 8 pi. A little bit less computational work, and we didn't have to go through the trouble of parameterizing this curve. Right, so Green's theorem gives us another way to avoid having to parameterize curves. The reason why that's important is that often the parameterization is the hardest part of the problem. Okay, so that's an example. Let's take a look at a few other examples. Okay, so we want to find this curve. So the function curve here is, that's an f, is pq, where p is x, y, and q is x squared y cubed. Okay, and the region that we're going to use is triangular. So let's make a sketch of it over here. X, y. We have a vertex at 0, 0. We have a vertex at 1, 0. And we have a vertex at 1, 2, right? Over 1, up 2. So this is the region here. So we have to sketch it. Okay. So this is a closed path around this. So we could define that to be positive. We'll go this way. Okay. So that this all works out nicely for Green's theorem. And what that means is I have 3 curves, right? And I'm going to have to parameterize every one of those curves if I do this directly. So let's get started on it. Let's call this C1, C2, and the C3. Okay. And we'll start with C1. Okay. So C1 is a curve this way. I have to parameterize it. The standard parameterization for a line segment would be R is 1 minus t times initial position vector plus t times the final position vector. So that's going to be 1 minus t times the initial position vector is 0, 0, plus t times the final position vector 1, 0, to go from here to here. And so that's going to be, let's see, multiplying this in, it's just 0, 0, plus t 0. So we get the position vector t 0, right? Okay. And that means that our derivative of that would be the derivative of t is 1 and the derivative of 0 is 0. And that means that plugging that into the function vector here, and I'll replace x's, sorry, not here, x's with t and y's with 0. Right, so that means this is going to be, this x becomes t, and this y here becomes 0. And this x becomes t, and this y becomes 0. So it looks like I have 0, 0 as my force vector parameterized with the position vector. And so if I do f dot r prime to get the integrand, f is 0, 0 dot r prime is 1, 0, which is going to be 0 plus 0 is 0. So when we do the integration of that value over the parameter, and the parameterization here would be 0 goes from, or t goes from 0 to 1 for a line segment, we end up getting 0. So what happens is that that this sums to 0 along this path. right? And that's because the force vector had, or the vector field had an x in both terms, so or a y in both terms, sorry. So since y was 0, it was 0 throughout. Okay, now we have to switch to C2. Let me change colors here. For C2, we have to parameterize that. So I have another parameterization. R is 1 minus t times the initial point here, which would be 1, 0, plus t times the final point, which is 1, 2. So that's going to be, let's see, 1 minus t and then 0 plus this vector multiplied out is 2t and 2t. So the position vector now is 1 minus t plus t is 1, and then 0 plus 2t, right? And so that means that my r prime vector would be the derivative of that, which is 0 and 2. And so the parameterization of the field would be x this time is replaced with 1, right? And y is replaced with 2t. And the x squared would be replaced with 1 squared, and the y cubed would be 2t squared, or sorry, cubed. So that gives me 2t for x and 8t cubed for y, right? Okay, so now I have to take the dot product of that with the r prime vector to get the integrand. So we have 2t, 8t cubed dot 0, 2, which is going to end up being 16t cubed, because this is 0 plus this times. And so that means we're going to be integrating 16t cubed for the function. We have to integrate that integrand, dt, over the t, and since we did a line segment, t goes from 0 to 1. So we would have, let's see, that's t to the 4th, 0 to 1, which ends up being, let's see, actually there's a 4 here, right? Because this would be divided. So yeah, 4. So it's going to be 4 times 1, 4 times 0 is 4. And so what that means is that along this path, the contribution to the circulation is 4. And then we have to parameterize the final path. So let's do that one down here. I'll use green for that. So we're going to do along curves 3, a parameterization for r, starting at 1, 1, 1, 2, and ending at 0, 0. So we're going to have 1 minus t, starting at 1, 2, ending at 0, 0. So this is going to be 1 minus t, 2 minus 2t, plus the vector 0, 0. So the final position vector is 1 minus t, 2 minus 2t, right? Okay, and then we would have, let's use, so that means the derivative would be -1, -2, right? And we would have to parameterize the function, and that's going to be, let's see, it was x, y, right? So x is 1 minus t, y is 2 minus 2t. And then this is x cubed, y cubed. Wow. Okay, you know what? There's actually an easier parameterization. This is becoming kind of cumbersome, so I'm going to back up and do a different parameterization. Instead of the standard line segment, what if we did this? What if we just said, this is the line y equals 2x, right? It just over 1 up 2. What if I just used x as the parameter? That would make the parameterization easier, and I think it'll make the field plugin easier. So what I'm going to say is, let's let x be the parameter, and then we'll just define y as 2x, or if we like 2t. But then that means we're going from x equals 0 to x equals 1. Actually, we're going from x equals 1 back to x equals 0 for positive circulation. So that means the parameterization will be from -1 to 0. I think this will make it easier since we don't have quantities to square. The derivative now would be 1, 2, okay? And when I parameterize, this is going to get a little easier. So x is t, y is 2t, x squared is t squared, y squared is t cubed, or 2t cubed. And see, you can parameterize in any way you want. You can pick an easy parameterization, or harder parameterization, this parameterization is easier. So I want to end up with 2t squared and 8t to the 5th. And so when I take the dot product now of that with r prime, and be 2t squared 8t to the 5th dot 1, 2. So that's going to be 1 times this plus 2 times that, so 16t to the 5th. And then our integral would have to be the integral of that, 2t squared plus 16t to the 5th dt, where the parameter goes from -1 to 0 to go in the correct direction. Okay. And if you trust me, after going through all that, you end up getting 2/3. So that means that along this path, it's 2/3. And then that means the total circulation here is equal to 0 plus 4 plus 2/3, which turns out to be, let's see, is it 2/3? Oh, I'm sorry, it's 10/3, negative 10/3. I'm sorry, looking at the wrong place in my notes. This is negative 10/3. This is negative 10/3. And when you sum these all up, you get 2/3. So you end up getting 0 plus 4 minus 10/3, which ends up being positive 2/3. So doing this directly is a pain because we have 3 linear paths. We have to have a separate parameterization for each. Find the derivative for the tangent vector, do the dot product, do the integration, and then sum the results. Green's theorem is going to turn out to be much easier here. And that's because we just have to do a single double integral. Okay, so let's do this with Green's theorem. For that, I'm just going to erase here. Let's say we just wanted to use Green's theorem here. Okay, so let me graph the region again. Right, the path is from here, to use blue, here to here to here. Okay, and if we define that, then we just have to say that this is equal to the double integral of the circulation, right? So the circulation is make sure we get it right here. It's dq dx minus the dp dy, right, over the area. All right, so here's the region we have to cover. And so now I just need to do a double integral. Well, let's first calculate what the circulation is. So dq dx minus dp dy. So q is this part with respect to x is y. And q is the second part. Let me label properly. This is dq dx dp dy. This is p, and this is q. So q with respect to x would be 2xy cubed, right? And then p, that's this one, with respect to y would be x. So this is the integrand for, this is the circulation expression for any point xy. So I'm doing a double integral of that, 2xy cubed minus x. And then for the area, we're going to stick with rectangular. Maybe we go in the y direction first. So that means we have to go from y equals 0 down here to y equals 2x up here. 0 to 2x. And then we have to go from x's from 0 to 1. So this would be the setup. And now we'll have to do this iteratively. So let's do the inner integral. I'll use black. The inner integral is the integral from 0 to 2x of 2xy cubed minus x dy. So the y is the variable. This is the only thing that's the variable. So I'm going to split this into 2 integrals. This one is y cubed dy. And I've got, this is just a constant, 0 to 2x dy. So this is cubed. So the antiderivative here is 1/4 y to the 4th from 0 to 2x times the constant 2x. And over here, this is just a constant. There is no y here, so it's just that constant times y. 0 to 2x So then we would have our 1/4 something to the fourth minus 1/4 something to the fourth. And we would plug in 2x here and 0 here. And then over here, we have our x, we have our two copies, something minus something, where we're plugging in 2x here and 0 here. And that boils down to, let's see, 2x. And then we have, let's see, 2 to the fourth is 2 times 2 is 4. 4 times 4 is 16 divided by 4 is 4x to the fourth. And then this is 0. And then this would be minus 2x squared. Okay, so I'm just going to multiply it all out. We have 8x to the fifth minus 2x squared. That's the result of the inner integral. Now we're going to do the outer integral from 0 to 1. Oops. Clear some space down here. Okay, so for the outer integral, we're going to do the integral from 0 to 1 of that. 8x to the fifth minus 2x squared dx, which is just 8 and then 1/6 x to the sixth minus 2 and 1/3 x cubed from 0 to 1. So you end up getting 8/6 minus 2/3, right? Minus 0, which this would be 8/6. Let's see, that would be 4/6. So it's going to be 4/6 or 2/3. So that's a much faster way to get to the answer 2/3 for the total circulation. All right, so Green's theorem, a big help here. We didn't have to parameterize curves. We just had to find one double integral, but we had to only find it for this little circulation expression. Okay, a couple more examples. Okay, evaluate this integral, x in the x direction, y in the y direction around this path from the line segment, circular path, or parabolic path. Sorry, this is a parabolic path. Y is 1 minus x squared, and then here. Directly and using Green's theorem. Okay, well, directly, the first thing we would do is check to see whether the function was conservative, because if it's conservative, then we have a zero path, zero line integral. So let's see, is it conservative? So let's find dp dy and dq dx. So dp dy, this is p and this is q. dp dy is 0. dq dx is also 0. So actually those are equal. This is conservative. And therefore, because it's a conservative field, we automatically know that this sums to 0, and we're done. Okay, so directly, not hard. If we did this with Green's theorem, we would first find the circulation, right, which is dq dx minus dp dy, which would be 0 minus 0 would be 0. So we'd be summing that over some area, and we know that when we sum things over 0, it's 0. So both methods quickly get us to this as 0. If we didn't check that this was conservative and we went through the trouble of parameterizing each of these segments, you could do that. It does evaluate to 0. If you're interested to see that, look in the posted filled-in notes, because I have that worked out that way if you didn't realize that you should check for conservative first. Okay, let's do another example here. Evaluate using Green's theorem along the positively oriented curve. They didn't give a sketch here. Let's actually see what the sketch is saying. It looks like I have two circles here, radius 1, radius 2. So I've got a radius 1 circle and a radius 2 circle. Along the positively oriented curve, where C is the boundary of the region between the curves. All right, wow, crazy. Okay, so technically there's a region enclosed here. Okay, and if you wanted to evaluate this, well, it'd be counterclockwise this way, right? And then actually this way, I believe, so that you're enclosing that region in that manner. Might have to double check that, but Yeah, we'll have to go along the curve. When we do it with the curves, we don't care about the direction, but they're just directly saying, hey, it's the positively oriented curve, so we don't have to worry about the arrows. But I believe it would be derived that way to indicate you're enclosing this region. All right, so we're directly using Green's theorem. So, I'm going to need to find the circulation. So the circulation is defined as dq dx minus dp dy, where this is p and this is q. So let's compute the circulation. dq dx would be 4x cubed, and then this 2 would come down, so we'd have a 4xy squared, right? That's this term, right? And then minus, wait, is that minus or plus? That's plus. Sorry, that's this term is plus. And then, actually, wait a second. This is this term here, okay? And then dp dy, so minus dp dy. dp dy, there's no y anywhere in here, so this is all a constant, so the derivative is 0. So the circulation is this, and we would go ahead and just integrate that over this region. So we know that that line integral there is equal to the double integral of the circulation over some area. Okay, to cover this area, definitely polar coordinates. We'll go this way. This would be from r equals 1 to r equals 2. So to set this integral up, well, since we're going to go polar, we have to replace things. X's get replaced with r cosine thetas. Y's get replaced with r sine thetas, right? So we would have to make this 4 times r cosine theta cubed plus 4 times r cosine theta times r sine theta squared, and then the dA will be r dr d theta. The setup isn't bad. This is going to go from r is 1 to 2, and theta is from 0 to 2 pi, but we're going to have to do some simplifying here on this integrand to see what's going on. So what do we get here? We've got we've got 3 r's multiplied. We have cosine cubed. We have a 4. We have 1 r here and 2 more r's here, so that's 3 r's. We have a cosine theta and then sine squared theta. And then I have the r on the outside of that, okay? This r multiplies all of that. So then what could I factor out here? Well, I could take a 4r cubed out, right? And 1 cosine theta. So let's do that. 4r cubed and 1 cosine theta, leaving cosine squared theta here, and leaving sine squared theta here. Okay, but sine squared plus cosine squared is 1. So this is 4r cubed cosine theta times an extra r. So it's 4r to the 4th cosine theta. Okay, so luckily there was quite a bit of factoring and things that happened there. So let me express the integral over again. We've got the integral from 0 to 2 pi. The integral from 1 to 2. Now the entire integrand, including the r from the r dr d theta, is 4r to the 4th cosine theta, dr d theta. And that means we could separate these because this is factorable. So we could write that as the theta part, which just contains a cosine theta. We have a 4, which can come out as a constant. And then we have from 1 to 2, this is a 1, of r to the 4th dr. Right? So we would have 4. Integral of cosine is sine from 0 to 2 pi, and then we would have 1/5 r to the 5th from 1 to 2. So this is going to end up being 4 sine of 2 pi minus sine of 0. And then this is going to end up being 1/5 2 to the 5th minus 1/5 1 to the 5th. Okay, but sine of 2 pi is 0, and sine of 0 is 0. So actually this term, it's 4 times 0 times something. So after all that work, it turned out that the sum was 0. Okay, all right. And yeah, so it just happened that the sum of all these circulations in here sum to 0. Some must be positive, some must be negative. Okay, now this is not a conservative field, right? I think if we were to check this, we probably could could have checked this. I don't believe this is a conservative field, right? The derivative, well, maybe. No, because this term was 0 and this term was not 0. So this is not a conservative field, right? But it's still summed to 0. So it's true that conservative fields, line integral along a closed path will always be 0. But it's not true that all 0 paths mean that the field was conservative. You could have a field where if I summed over different paths, I wouldn't get 0. But on this particular path, I do get 0. All right. And then one final example, okay? Evaluate using Green's theorem, and they're giving me another try and get a region. So here's my P and my Q. We'll do Green's theorem. So let's do the, I'm not going to bother with the multiple paths approach. We're going straight to Green's theorem, 0, 0 to 0, 0 to 2, 6. So over 2, but up 6. 1, 2, 3, 4, 5, 6. Okay. 0, 0 to 2, 6. Okay, so that path. And then the triangle from there to there. And then 2, 6 to 2, 0. Okay. And then 2, 0 to 0, 0. So it's this path right here. All right, now one thing that's interesting is that path specifically is defined clockwise. So this is the negative of a counterclockwise path. So at the end, we're going to have to multiply our result from Green's theorem with a negative to account for the fact that this path is actually, they didn't state here the positive path like they did in this problem. So we have to determine whether this is a positive or negative path. And so we're going to multiply by negative and we're done. Okay, the circulation is partial q with respect to x, my partial p with respect to y. So this with respect to x, the 2y is a constant. The derivative of sine is cosine. And then here, p with respect to y would be 2y, and then the cosine x is a constant. So is that right, that turns out to be 0? That's not what I had here. Oh, yeah, that's right. qx py would be 2, is that right? 2x. For some reason, I'm getting something different than what I did before here. Oh, I missed the x squared. That's why. Let me just do that again. I didn't see something here. So we need dq dx minus dp dy. If they turn out to be the same, then we know it's conservative and we stop. But okay, q with respect to x, that includes this x squared term. Okay, so we have 2x and then plus the derivative here, which was 2y cosine x, and then minus this, which would be 2y cosine x. Okay, so these are not the same, so it's not conservative, and that means we have some sort of expression here. But because when you compute the circulation, these and these cancel, it ends up just being 2x. So I have to do a two-dimensional integral of the integrand 2x over an area. We're going to choose to go rectangular, y first, which means we're going to go from y equals 0 down here to, this is over 2 up 6 or over 1 up 3. So this is the line y equals 3x. So we're going to go from y equals 0 to y equals 3x. And then we'll cover this with x's from 0 to 2. 0 to 2. All right, so to finish this off, we would get the inner integral is 0 to 3x, 2x dy. But while we're treating y as the integrand, the 2x is a constant. Y from 0 to 3x is going to just be 2x times 3x, or 6x squared. Okay. And so the outer integral is from 0 to 2 of 6x squared dx. So that's going to end up being, let's see, it'll be 2x cubed, right? 2x cubed from 0 to 2. So it's just going to be 2 times 2 cubed minus 0, which is 8 times 2 is 16. But that's for this direction, Green's theorem is always for a counterclockwise. So because they specified to go in that other direction, the final answer is negative 16. All right. All right, and that's the final example. So hopefully that should give you plenty to be able to try the homework problems.